Hello.
In this session is Archana Pai, and she's going to talk about source optimal tracking and LISA beamforming.
Yeah. Hello. Sorry for this. Where is my pointer? Hello. Is it okay now? Can Badri hear me? Okay, fine. Right. So let's. This talk is purely on the about the LISA, and so the astrophysics will talk at the end of it. So let's basically talk. Let's switch gears a bit and talk about the instrument. So so basically, as all of us heard in Bernard's talk, that the dominant noise source for LISA is the laser frequency noise source, and in order to remove the fluctuations of the laser frequency, you need to implement TDI. And there are three independent TDI data streams which give which has noise completely uncorrelated. Now the question which we ask in this is related to the network, that these three data streams have different frequency response and the antenna patterns. So can we use them to optimally track a particular source in the sky? So this is sort of a summary of beaming, but we'll talk about it later. So the plan of the talk is the following. I'll just briefly talk about the TDI just to remind you, and then I'll talk about the three data streams which people talk about, call it as AET, and then I will address the directional optimal issue, as how do you combine them by switching various data streams as source moves in the LISA sky. So right, so this is a schematic of LISA. So it's the LISA triangle. Okay, 1, 2, 3. There are spacecrafts at the corner, and then you send the laser beam along each arm. And so let's say we are considering the beam Doppler data streams at spacecraft 1. This laser noise at 3, which is sent to 1, okay, and is wet on the onboard laser, and this is the data stream which comes out. This is the laser coming from spacecraft 2 and going to 1, and it's again wet on the onboard laser, and this is how you get. So this is how you get the 6 Doppler data streams. Now we ask the question that, so this is like I give order of estimates, like how much is the laser noise in the TDI stream. So let us say that you have, we take a simple design, which is a Michelson, which all of us know. So let us say you have a laser here, and then you this is a Michelson, so there is a beam splitter, you allow the laser to pass in here, and then you combine here. So let's assume that the two arms are not equal. So the laser the two interfering lasers, they travel unequal distance when L1 is not equal to L2. Whereas if it is equal, then automatically you cancel the laser noise. So so here is sort of the estimate for LISA. So let's say that you have an arm length of 10% inaccurate, like if L1 and L2, the difference is around 10%, and these are the LISA specifications. So the laser noise you expect is something like 10 to the power minus 16 per root hertz at 1 millihertz, and for the LISA sensitivity we need 10 to the power minus 22 at 1 millihertz. So we are something like 6 orders of magnitude high, and of course we need to suppress it. So the idea is very simple of TDI is the data streams which you are going to interfere, you make them basically travel the same light travel time, and then you combine them, and that's how you basically get rid of the laser noise. So that's a simple idea. But since you have 3 arms and 6 Doppler data streams, you can basically get infinite number of such data streams in which you can cancel the laser noise. So this is one simple Lisa-Michelson combination, where what happens is, so this is how you write it mathematically, whereas here I demonstrated how. So let's say you have a laser noise here, which we call C1, C2, C3 at the three laser streams at the three spacecraft, and when you go when you take this term, basically you make the laser travel along L3. Okay, it's as if you have sent the beam here and reflected it back. Okay, similarly this term shows that you send the beam here and reflect it back. So automatically this term sort of cancels the laser noise at C3, and this term cancels the laser noise at C2, so which is shown here. So let's say these are the two delayed data streams. So this is shown by sum of these two, and you see that this cancels C2 and this cancels C3, and when you combine them, it cancels C1. Now with this simple idea, you can get the zoo of so this figure I have taken from Michele's paper. It's a very nice figure, and where it shows you all possible laser noise free combinations by just taking the beams around. So this is a simple Sanya combination, where you take the beam around and then you take another beam around and then you interfere them, and then you subtract the noise. This is the symmetric Sanya combination, and then you have other TDI combinations which you can use for the monitoring, or this is the unequal arm Michelson combination which I showed before. So here you see that there are large number of TDI combinations which have different frequency responses and different antenna buttons, which I will show you later. Now the question is, which are the data streams you should use then? So it was shown that you can basically treat these guys, so alpha, and then you do the same thing cyclically. So you do it at each second and third satellite. So you get 3 data streams, and then the fourth one, which is this symmetric Sanyas, which is insensitive to the gravitational waves at the low frequencies. And with these 4 data streams, you can basically get the whole combination of all possible laser noise data streams. Now, so here you see the sensitivity of the streams. So this is the Michelson combination which I showed earlier, and this is the symmetric Sanya combination, which is absolutely insensitive to gravitational waves. So the idea is, like, the more symmetry you have in the system, then at low frequency the combination cannot make distinguish between whether it's a laser frequency noise or whether it's a gravitational wave, and it's sort of it's completely insensitive at low frequency. That's what you can see here. So for example, the symmetric Sanya is completely insensitive at the low frequency, and alpha has some symmetry, so which you can see here, whereas Michelson, you are just using the 2 arms. Whereas at high frequency, the lambda is comparable to the size of the arm length, and hence you start seeing the geometry of Lisa and the symmetries of the data streams in the combination. So for example, at 60 millihertz, which I think you can see here, corresponds to the frequency corresponding to the arm length of Lisa, and you can see the peaks around the multiples and so on and so forth. Right. So those were the streams which I showed, that the zeta and Michelson and alpha, and now these are the 3 streams which people were mentioning, which are basically AET, which no, okay. So the streams which gives you sort of bounds on all possible data streams. So in a sense that any, I think this is not working. Fine. That was real. Okay, so right. So the three combinations which are AET, they are they basically bound all possible laser noise data combinations, which means that so this is the key combination, which is zeta. Then these are basically AE combinations. So if you take any other combinations, okay, they will basically they will sit in between all these combinations. So they sort of are optimal in the sense that everything will sit in between AE and T. Okay, so that's, and the noises in them are independent, so you can use them as sort of a basis. Right. So now, so we know that. So we know that these three are basically the basis combinations which you can use. Okay, in which contains the Lisa noise is also uncorrelated. Now we ask a question that how is the response in the sky, like what is the antenna pattern? So these are the different strings. So this is basically E, A and T, and they at low frequency. So this is, I've taken 10 millihertz. So at low frequency, basically they act like Michelson, so like a two-arm Michelson, and of course the third combination is insensitive, and you see that all the three, even alpha, beta, gamma, which I showed the symmetric Sagnac, they have a Michelson response. So basically all the since this guy is insensitive and low frequency, you cannot make distinguish. I mean the responses of all the data streams is basically like a Michelson, okay, which is this quadrupolar, which is the same thing as the ground-based detectors. Okay, but as the frequency increases, then so this is at 25 millihertz. Okay, so as frequency increases, you start seeing the structures and the geometry of Lisa basically. So this is the same E, A and T. Still this guy is insensitive, okay, but you can see these, they do not have a symmetry anymore. I mean there is a symmetry, but they do not have the translational thing which we saw in case of Michelson. Yeah. Right.
Yeah, I'm just commenting on surprised that there's such a large volume inside.
That indicates the orbit factor.
Yeah, this is insensitive. Yeah, this is insensitive. I'll show you the integrated one. Yeah. Yeah, this is instantaneous.
Yeah, of course it happens, right?
Yeah. Right, so this is for 25 millihertz, and if you go further, and this is for 50 millihertz. So here you see that the AE becomes insensitive at 50 millihertz, whereas T, because at 60 millihertz, okay, okay. Okay, so now let's so if this is the thing, then we ask the important question that how do you point. So if this is the antenna patterns, then which is the combination which we adopt if we want to look in Lisa sky in a particular direction. Okay, so this is the answer. So let's say you have AET, okay, and you're looking in a particular direction in the sky. So at a particular frequency and at a particular direction, okay, this is the combination which I want to choose, where the coefficients are not any arbitrary, but they are the one which will point in that direction. So basically this optimal directionality gives rise to 3 data streams, okay, and you can realize them geometrically. Like if you have 3 data streams, then you have 2 polarization vectors, which is S plus and S cross, and they sort of form a polarization plane. So this is the signal is sitting on S plus S cross plane, okay, and then you are choosing that combination which gives you the maximum SNR, okay, and this gives you a minimum positive SNR, and the one which is orthogonal to the plane gives you 0 SNR. Okay, so these are the 3 combinations. Now this is instantaneous. So if I want to look in a particular direction at a particular time, so as the source moves in the sky, okay, yes, shown here. So for example, if you take the source in the bicenter which is at zenith, okay, that will is shown by the circle. This is shown by this circle in the LISA sky, okay, and the idea is that at each point you basically choose that particular optimal stream and then you track the source in the sky, okay. So this is the tracking, okay. So this is the improvement which I will come back to it later. So as we know, I mean, as you expect that at low frequency the tracking, so this is, so now I am tracking, so this is basically I am tracking with all the data streams. So this is AEP, this is the integrated one, and this is I am tracking with the plus, cross and 0, okay. At low frequency, of course this guy is not there, so they give equal responses, whereas you go at high frequency. So this is the one which gives you the maximum. This is the one which, if you combine these 2 guys, then this is what you get, okay. And this is the one which shows null, I mean shows 0 SNR in that particular direction. So the network of these 2 basically complements the null, whereas if you look at this data stream, then which is basically the network of these 3 combined, then they see the entire sky, okay, whereas if you look at the network of this, then you just see the one which you are tracking. So I am tracking here the direction which is 60 degrees and 200 degrees in barycenter. So I show further for 60 millihertz. This is how you. So you expect, of course, as you increase the frequency, the beaming is better. So this is what we call beamforming, and it improves with the frequency. So this is what. So this is for plotted for different frequencies from 10 millihertz, 25 millihertz, and so on and so forth. Right, and I mean there is one more thing in this which is also sort of expected, is that this beaming is not monotonic. So as you go at the high frequencies, then of course the LISA geometry plays a role. So the symmetric Sagnac plays more role in when it is a multiple of 60 millihertz, and that's the time where it's more symmetrized and the resolution increases. So sort of you don't see a monotonic thing, but you see peaks at high frequencies, and which is basically what we also see in the noise curve, LISA noise curve. Okay, so it's very short presentation. So this is sort of a summary. So basically you have 3 data streams which you can if you want to point a source in a particular sky, you can optimally do it. And then you have these 2, when you combine, okay, they sort of complement the null stream, and they give you the same SNR as if you track with in the network of AEP. So there is no harm in using this thing, because you're doing, first of all, you're doing all these things in software. So you will just store the data, and then you in the software you can choose a combination and then switch them, and then add them in network and see whatever you want. And this scheme is, for the moment, is for the monochromatic source. So the idea is you pick a particular direction and you pick a particular frequency, and you ask a question that which is the optimal stream. Okay. So it can be extended for the frequency evolving sources. So currently with stars, we are thinking of whether there are any possible applications for IMRIs or MRIs. MRI, I think the frequency is very low, but maybe for IMRIs there can be a possible application, like doing it hierarchically. Right, first you do all the data analysis on the switched data streams, and so that's okay. I want to show one movie before that. Oops. Yeah, it's just a movie how it tracks. Oops, no. No. But I can show you in my laptop. No? How much time I have? Okay.
Maybe we'll go to questions now.
Okay, yeah, sure.
The way it's setting up. I mean,
yeah, sure.
You can ask the question while it's setting
yeah,
up.
Sure. Sure.
Okay, so thanks for talk. Okay, still in here, we want to see a movie, but we're not sure we can show a movie, so we're trying to figure out if we can actually show the film. Take questions.
Very simple question. What are your combinations of different polarizations? Is that correct? The optimum linear configuration.
Yeah, so for the moment, here, yeah, I mean, I've assumed that the sort of the average of the polarization here.
But you know what I'm saying. If you point the direction of
Yeah.
your optimum combination is going to be different.
Yes. Yeah, so this one, okay, so the data streams we had obtained in 2003, okay, but the beaming is a new thing. So the yeah, it was yeah, because we had this discussion with Massimo regarding the switching. I mean, that time when we got in 2003, and then basically the argument was that why do you use switch combination? I mean, you can do might as well with AET, because you could just combine them and then you track them, and then you can obtain the same SNR as the switch one. But the advantage here, I mean, if there is, I mean, that we have to investigate, is that if you do AET, okay, and track it, then you see the entire sky. But if you want to, let's say, I don't know, I mean, in IMRIs or something, if there are some 2-3 sources, and if you want to, one is looking in this direction and another direction, then maybe you can use switch ones and like sort of put a consistency check, and then you use a null stream on that, because this gives sort of the same SNR, but it has the advantage that it is beamed. So yeah, sure, okay. That's the movie. Yeah, so this is just how the tracking works. I mean, it's so I'm. Oops. Sorry, just a minute. Yeah, so this is how it works. Let's play again, maybe. Yeah, so I'm tracking the source which is at this point, and you see as is integrate, it sort of just coherently adds up at that particular direction, but it sort of averages out the other direction. Okay.